presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody, I hope everyone's having a beautiful day. I want to welcome you on today for today's lecture. So if it's your first time being here, my name is Dan or Daniel. For formalities it's Dr. Page, but just call me Dan or Daniel. And for those that, I guess, it's already almost halfway into January. That's wild. I was going to say Happy New Year, but we're already kind of just zipping right past through. But anyways, I hope you're having an amazing day. And beyond that, I also want to tell you, if you enjoy what you're seeing so far, make sure you tell your friends to come join the fun. We have ourselves a blast over here. Other than that, if you want to support our work, this work beyond just watching, liking, and sharing, or telling your friends, because please, a lot of people just don't know we exist here, so please, it'll be a massive, massive help if you tell somebody, just even one person, hey, look, you want to learn about computer science or that mathy, the M word, that stuff that goes along with it? There's this place you could go where you can learn it for magnitudes cheaper than the universities. It's a place that exists. So please come on down. Everybody's welcome. But anyways, that being said, this work is supported through Patreon, Subscribestar, so please consider supporting on Patreon at patreon.com/pagewizard. I have all sorts of rewards over there. Also, after today's lecture, these notes, the ones that I'm using as a basis for today's lecture, will be available there as an educational resource for you to study from our lesson here today. Also, I thought I would wear something a little different today. I'm nothing too much substantial, I swear. But I got this pin over the holidays from a fan. It says "I love onions" and it has this lovely green character on it. So I thought I would wear it today, just because when I get cute things like that, I gotta share them with people. You know, it's part of the fun. So I thought just to add a little extra salt and pepper on top of our lecture, I thought I'd throw a little bit of our green friend in here too. Because guess what? Onions are pretty awesome. Just, they have layers. So, if anybody asks you why there's a random Shrek pin on my suit, that's why. It's because a fan had given it to me. So I'm going to wear it this week. So if there's any time you're watching this in the future, whether it's a segment from today's lecture or just you're watching this in the future, it just was a fan that gave me it, and it just says "I love onions" on it if you can't read it carefully. And I just thought it was fun. So anyways, other than that, one other piece of news is that I will be putting together the mailing list site, so that if you're wanting to sign up for the mailing list, because I am working on the new website, it's very slowly happening, but most certainly it is happening. So this year, I'm going to be putting more of those machinations in place, so that people can learn computer science through courses, as opposed to just learning directly from me. There's also going to be options for those that prefer more of a course-oriented approach, whether it be self-driven or, and I'm hoping to have it where we can have lectures kind of like this, but they're delivered through a course where it's us together. But we'll see how it plays out. I want to see what you think. So please, if you have any thoughts about any of this stuff, please let me know. I'm happy to hear your feedback. But either way, we're ourselves a blast on over here. And I think we're going to get started rather than me going into a lot of details here today. I'm just going to check the chat, just make sure there's anything interesting going on in the chat. One other remark, I always like to bring this up, is that I can hear audibly anything that pops up in the chat. So whether it be so I can hear and I can see the chat. So if you're in the chat and you have a question, please don't hesitate to ask. If it's a small thing, I'll clarify it. If it's something a little bit bigger, I might hold off until we get to the kind of like a next kind of middle point in the lecture if it's a little too far off. But I usually try to address questions that are in the chat. That's usually a big thing for me, is making sure everybody can understand. Because if somebody has a question, usually it might mean somebody else may have the similar question. And it tends to be helpful in a lecture format, because it's not just what I have declared as the topic, it's also how together we make the lecture. And that's a big part of how I see lectures, is that it's not just simply I dictate things to you, because keep in mind, these are just notes to help you learn. This isn't simply what I use. It's just an element of it. Just like when you go see a stage play, it isn't just simply merely the script that you get from the performers that is being on display. That may include other contexts that you wouldn't normally see when you actually watch the performance, which might bring more things together. Either way, it has more stuff in here as well. So keep in mind there's more examples and things like that as well. So if you're curious about these things, please consider supporting on Patreon. We have very, very low tier with high rewards. So please consider. And it helps, keeps the lights on in the lecture, the lecture area we have here, our learning zone. So help the learning zone continue by supporting on Patreon. That's just my other way I could kind of just weasel that in there. So, sorry, I'm just having a little bit of fun. But let's get into things today. So just a couple of things I wanted to talk about before we get into today's main topic. I just wanted to revisit a couple of key ideas. I'm going to avoid writing too many things on the board. Instead, I'm just going to remind you of a few concepts. So, and it's going to be kind of helpful for me to do this. So imagine you have a set, and a set is it's going to have some collection of objects in here. We're not going to care about there being duplicates, because we don't really care about the duplicates. We're also not going to care about the order they're in. You can imagine almost like a bin with just some things in it. Imagine each one of these is a distinct object. And I want to know different things about how I might arrange the objects. I may also be interested in what exactly goes in here and how many there are and how I arrange them. So for example, I may care about, if I were to lay out these objects in a specific order, how many ways could I order them? Likewise, I could be interested in how many possible ways I can group the objects. So please keep in mind that that's kind of the central idea behind a lot of the combinatorics we talked about before, when we talked about permutations and combinations, respectively. So we're going to be revisiting this idea of combinations as a part of today's lecture. So please just keep that in the back of your mind. And if you've never heard of combinations, don't worry. Some of the things I'll talk about here today will remind you of these facts, or you've never heard about it. You're welcome to check out a previous lesson on this topic, where actually we derive the formulae that you'll see in today's lecture. So if you want to know, oh, how do I know how many K combinations there are? We actually did do that in a previous lecture. We actually derived that formula from just purely combinatorial ideas based on permutations and how many there are of those, minus all the repeats, right? So, so we talked all about how to do this. So if you're wondering more about that, we previously talked about this. So this is more of a recap. So let me get the chat off of here. But today we're going to be talking about some more combinatorial relationships. Namely, I'm going to revisit what we talked about as the number of K combinations. So let's talk about another combinatorial relationship. So we're going to revisit this formula that we came up with for the number of K combinations. So another combinatorial relationship. So we're going to explore a little bit more about K combinations and how many there are. And there's actually a relationship that I suggested to you previously that I want to now spell out more explicitly as an actual true property that does exist. So previously, we derived a count for the number number of subsets of size k from a set of size n. From a set of size n. So we have n objects, for example, and I want to know how many ways you can group those n objects. And we define this, that as n choose k, right? This is how we wrote it before. But I'm going to define it more carefully. Let us define it more carefully. So I'm just going to add a little wrinkle to it, just because it makes it a little bit more convenient to have a few edge cases covered. And it'll make sense within this combinatorial way of looking at this idea of n choose k, or what we're going to refer to as the binomial coefficient. Or sometimes I will colloquially refer to it as the choose function, because it is a function and it has two parameters and all this stuff. But a lot of people, they'll say it's n choose k. They'll talk about it as the number of subsets of size k of a set of size n. They'll talk about it as a binomial coefficient. But you get my point. So what is n choose k? So given non-negative integers, n and k, the binomial coefficient, and you'll wonder why it's called that. We will eventually touch upon this. The binomial coefficient, read as n choose k, it's often denoted as follows. So it's often denoted, as we already stated over here, as this notation, this choose-based notation. It's also written as C with parameters n and k, or sometimes it's even written like this, where you have subscripts n and k with a big C, is as follows. So there's two possibilities that can happen with n choose k. So the first possibility is that whenever k is less than or equal to n, there's actually an explicit meaning within this combinatorial one about the subsets, the one exact formulation we derived previously. That is, it's n factorial over k factorial times n minus k factorial whenever k is less than or equal to n. So remember, this is just simply as we defined it above, right? It's just the number of k combinations of a set of n elements. Right? There's nothing surprising about that. What I'm going to do is I'm going to define n choose k to be the value 0. Otherwise, whenever k is strictly bigger than n. So you might ask, Dan, why would it be 0 in this case? Well, I want you to think back to this, what n choose k is, as we defined it up here. So if k is strictly bigger than n, it's looking a little like an H. Whenever k is greater than n, what does this mean then? So it's the number of subsets of size k from a set of size n. So if k is bigger than n, then I'm asking for the number of subsets that are bigger than n. So there's got to have more elements than there are elements in the set, right? But how many of those are there? There's 0 of them. So defining it like this is rather convenient for our definition, but also makes a lot of sense from a combinatorial standpoint. So there are no k combinations There are no k combinations in this case. Right? So this is how we're going to define this. And let's do an example. Let's do an example, just so we can try it with some values. Okay, so what we're going to do is we're going to consider the following set. What we're going to do is we're going to consider the set A that has 4 elements in it. 1, 2, 3, 4 elements, A, B, C, and D respectively. So that means that the size of this set is 4. And now what we're going to do is we're going to try different values of K, just to see what exactly is going to come out of this n choose K business and what it represents. So we're going to make a little table here just to kind of help us play around with this. So we're going to have K. We're going to have a column for the subsets, so like the actual subsets of size K. And then we're going to see what n choose K is for that particular value. So first, let's try when K is equal to 0. Well, how many subsets of size 0 are there? You should expect there's only one, right? What is that called, though? There's only one subset of set A, or any set, with size 0. It's the empty set, right? It's the empty set. It's the empty set. And let's figure out what n choose K is. Well, it's 4 choose 0. Let's put in the definition. Since K is less than or equal to n, it's 4 factorial over 0 factorial times 4 minus 0 factorial, which that's just, remember, for 0 factorial is just 1. We talked about this previously. So that means that it's just going to be 4 factorial over 4 factorial, which is equal to 1, as you would expect. Let's try another value. Let's try K is equal to 1. So let's try to enumerate all possible values of K where K is less than or equal to n, because otherwise it's just 0, right? Well, how many subsets are there of size 1? Well, let's try using the formula first this time and see if it matches exactly what you came out with. So think about what they would be. So 4 choose 1, that's just 4 factorial over 1 factorial times 4 minus 1 factorial. So this should be what? It should be, so usually a trick when you're computing these counts of K combinations. One tip that commonly you'll find is that you try to exhaust the numerator such that it cancels out one of the denominators and then simplify. So I'm going to write 4 times 3 factorial, because the denominator, I have a term that is 3 factorial. So I have 1 factorial times 3 factorial. So 3 factorial and 3 factorial. So 1 factorial is just 1. So I end up with just 4. Is that the number that you ended up getting? Yeah, there should be 4 of them. So what are the 4 subsets? Well, let's see. Just got A, B, C, and D, right? So it should just be the 4 subsets, each one with each, I just pick off one of the elements from each. Right, that's it. So that's K is equal to 1. Not very interesting. Okay, let's look at K is equal to 2 then. Well, In this case, we're going to pick off 2 elements from set A, and we're going to see how many we could do of this. How many subsets of size 2 are they? So how many are there? Well, I'll just calculate this out first, and I'll let you think about what this would be, what this list of subsets would be. So I have 4 factorial over 2 factorial times 4 minus 2 factorial. I'm going to use the same trick I did before. So I have 4 times 3 times 2 factorial. Then I have 2 factorial on the bottom like this. And then notice that those cancel. And then I have 4 times 3 divided by 2. Because 2 factorial is just 2, right? So what happens? So remember, 4 is 2 times 2, right? So 4 divided by 2 is just 2. So I'm just going to end up with 2 times 3. 2 times 3, which is equal to what? It's equal to 6. So there should be 6. So let's see here. So now let's talk about what the would be. It's, well, we have AB, right? I pick off AB. Then I could have AC. I'm going to just start off by picking the first element, and I'm going to try to lump it with each one of these. Then I'll do the same thing with the second one. I'll try to lump whichever ones I have not accounted for. Remember, it's not the order that matters here. It's which subsets are together. Which elements in the subsets, to be a bit more precise. So I'm just going to sweep through here. I'm going to have AB, I'm going to have AB, AC, AD. Now next I'm going to have BC, right? BC. Okay, so I have BC, then I have BD. And then I would have, so I'm done enumerating over B. Then now I just have CD. And look, I have exactly 6. Exactly 6 as you expected. So here we go. So now we've done k is equal to 2. Let's see what k is equal to 3 does. Now, rather than calculating it out like this, let's just see what happens. We're going to use a similar technique to have how I'm going to enumerate these subsets of size 3. I'm going to start off with ABC. Then I'm going to shuffle appropriately with my elements so that I'm trying to capture all the ones leading. I'm just going to start off with using A as many times as I can. So I have ABC, ABD, ACD, and I have lastly one more, I believe, BCD. There's 4 of them. Let me just add some lines here. Make it a little easier to see what's going on here. Okay, so let's confirm that we've captured them all. So I got 4 factorial over 3 factorial times 4 minus 3 factorial. Well, that's awfully interesting. Well, let's see what happens. So I end up with, I got 4 factorial, 3 factorial. This ends up just being 1 factorial, right? So this is no different than me writing 4 times 3 factorial over 3 factorial times 1 factorial. 1 factorial is just 1, right? But the 3 factorial and 3 factorial, they cancel out with each other there. Cancel terms, and I end up with a 4 again. That's interesting. It's awfully interesting. It's interesting. Interesting. Now let's try our last value, because when k is 4, that's equal to n, right? So this would be when I write down 4, choose 4. So how many subsets are there of size 4? Well, surely it includes all of the elements, right? That includes all of them. So that's all 4, so that's just one subset. A, B, C, D. So I have 4, choose 4. So that's 4 factorial over 4 factorial times 4 minus 4 factorial. which this ends up being 0 factorial, so I end up with, again, 4 factorial over 4 factorial, which is equal to 1. Interesting. Interesting. Does anybody see anything interesting going on here? And I assure you it is not a coincidence. It is not a coincidence. I'll give you a hint. I want you to look at this. I'll go 1, 4. We have 1, 4, 6. Then I have 4, 1. Okay. What I want you to do is imagine I have the 1 and 4, and I mirror it over onto this side, or basically about the middle. Imagine I go about the middle, so that's the middle in this case. If it has 2 in the middle, then I would mirror across that. So imagine I have these first 3, then I'm just going to mirror it like this. And you see that they're actually the same. There's a symmetry here. Very fascinating. That is not actually a coincidence. That is actually a property in this case. That is actually something you should expect to exactly happen. So please notice that this and this, these two, they mirror. Specifically, this entire list is a mirror. It's like a mirror image over the middle. So it mirrors over the middle, in quotation marks, quote unquote, the middle. So now you could verify that this is in fact true algebraically, but I want to use a combinatorial argument to show you that this is not just by happenstance the way we have these subsets. There's actually something very fascinating going on here that involves these different subsets. So what we're going to do is we're going to come up with something called a combinatorial argument. We're going to take 2 sets, we're going to talk about those sets, their sizes, and then argue that those 2 sizes are in fact the same by doing what is easiest to see if 2 things are the same size. You pair them up. So I'm going to make an argument about these objects that talk about the sizes of them. And if I know the size of one of them and I know the size of the other one, if I can pair them up uniquely, then they have to have the same sizes. So here's a theorem. So for any k, we'll go n and k. For any n and k, which are going to be positive integers. So these are going to be positive integers, but I'm also going to allow n and k to be 0. So these are going to be non-negative. So I'm going to include 0 as well. So that's what this means. It's the set of positive integers with also 0. So I'm performing a union operation to keep these two together. So this is the set of non-negative integers, as we discussed previously, where k is less than or equal to n. Remember, this is that case that we talked about. So that's the first of the 2 cases. So here's the claim. N choose k is in fact equal to n choose n minus k. That symmetry that we noticed is not a coincidence. It's in fact a true statement. Okay. So do you notice that if I make k big enough, it ends up that it just sort of just maps into itself in some way. So let's see what that means. There's a very simple argument for this, and I'm going to hopefully expose it to you formally, and then I'm hoping to give you a high-level intuition as we explain the argument, okay? So here's the game plan. I'm going to create 2 lists. I'm going to have a list of all the subsets of size k that correspond with this count. Then I'm going to create a second list that's going to be paired up with this first list. That's going to consist of subsets of size n minus k. And I'm going to show you that these 2, in fact, are the same in their size because of the way I'm going to construct the second list. So consider any set A with n elements. Now, what I'm going to do is I'm just going to enumerate all of the possible subsets of size k. So I'm just going to give the number of these a name. Now, it's not going to play a key role in the proof. It's just going to make it a little easier for us to explain. And you can figure out as you're going what r should be by the end of it. Suppose A has r subsets of size k. Of size k. So I'm just going to list them out, listed as B1, B2, so these are just names I'm giving them, B3, all the way up to BR. So this is a list of all of the subsets of size k. So it's just like when I went through this example over here, I just picking off that k, it's one of these rows where I took the column and I said, okay, those are my subsets. I'm just listing them out. The order they're in, it doesn't matter. So construct, so now here's how we're going to construct the second list that we're going to have. Construct a second list of subsets by pairing subsets of the first. So by pairing subsets. So here's the construction. For each I is equal to 1, 2, 3, all the way up to R, what we're going to do is we're going to take whatever we had in that subset, we're going to take A and we're going to remove whatever was in that subset. So watch this. So include A set minus BI. So just to clarify what this is a set difference, or I'm taking, this is a set difference right here. I'm taking out all the elements in BI that would be in A. So let me just state that for those that have not seen this notation before. Sometimes people write it as a set difference as a minus, which on a set, remember these are two sets, technically speaking. So which contains, so let me just clarify what this is, which contains all elements of A not in BI. And as a result, since I have a set of size n and I take away k elements from it, how big is the subset? It's n elements, I take away k of them, so it's n minus k many elements, right? And has size n minus k. So as the first list contains every subset of A. So this is very important for the construction. The first list contains every subset of A of size k, right? Of size k. The second list, as a result, right? The second list contains every subset of A of size what? N minus k. Right? Because all I've done is and this is very important for the argument because I'm going through every single one of the subsets of size k. And I know I'm getting subsets of size n minus k. Remember, I'm going through all of the ones of size k, and I show you how to build a subset of size n minus k. And it's all of them because otherwise there's no way you can have ones that aren't within this list of this given size. So I'll let you think about it. If you're not confident in this observation, I encourage you to go to our example over here on the right and try it and see if you can take a subset. So take a list from subsets of size k, so pick off a k, and then just simply see what happens if you take A and you remove all those elements and see what list you end up with. So now, the first list contains, so now this is where I just point my finger at things and say there's this many in this one list, there's that many in this other list, so it means it have to be equal, right? The first list contains all subsets of size k of A and the second list has all subsets of size n minus k. The lists have the same number of subsets, right? That is the number of subsets of A, the number of subsets of A with size k. Well, how many of those are there? There's n choose k many, right? By definition, equals the number of subsets of A with size n minus k. Which, what is that? It's n choose n minus k, right? And that's the proof. That's it. So there's a very intuitive explanation for what's going on here. Whenever I pick out a subset of a size k, there's going to be another subset that exists where you've chosen all the other elements, the n minus k many of them. So that's the intuitive explanation for what's actually happening. So I encourage you, if you're not sure about this, go back to this example we have with our table and try using how we constructed these two lists. But yeah, no, so pretty fascinating property. So are there any questions? Any questions at all? Don't be shy. So for us, what matters here for this discussion is that we varied over k. We're going to see that now when we start varying over n, something interesting also happens. I'm just going to go grab a different marker, just in case, because we're going to be doing a lot of drawing next, and I might need also a different color. Actually, I may need a couple different colors, so I'm just going to make sure I have a couple different colors on hand. Okay. So it appears that we don't have any questions. It seems rather quiet here today. That's okay. Let's I'm just going to erase the board. Just going to erase the boards here, and then this is actually where we're going to be transitioning into our first main topic of today. Because now that we have this property in place, we can then talk about what happens when you start varying n. And there's a very fascinating property that starts creeping out for sufficient large n. I'm just going to fix our camera. It appears that just something funny happened. Let me just fix that. Haven't had that happen in a while. So I'm going to cross our fingers that we didn't lose any fun stuff in there. There we go. That should be better now. Let me just make sure. Just want to make sure. I'm just going to do a quick check. I haven't actually had that happen in quite a while. I remember when I first started setting things up carefully in our learning zone, I'd run into that a little bit more often. So I thought it was interesting that that happened. So I'm crossing our fingers that we didn't lose anything in that process. I don't think we did, but I'm not sure. We got a red marker. I already got a red marker here. Let me just put this one over here. Okay. So the next construction we're going to run into, some would call this a mathematical structure. I'll describe it more constructively, but that's sort of the computer scientist in me. I sort of see a lot of these things as just a thing you can effectively build in an algorithmic way. So let's see here. Yeah, because we're getting into some fun territory next. And it's going to require me to draw a really big picture, so I'm tempted to actually start our discussion over... Do I have enough room on this board? I'm going to do it on this board. But I'm going to need to make sure I make a lot of room on this board, because we're going to be doing a lot of hard work on this table that I'm going to build over here. You thought the other table was quite exquisite? This one's going to be fun. So anyways, so previously we talked about the relationship that n choose k has as we vary k. We noticed that there's a symmetry that occurs based on whether you pick a subset of size k versus the subset of size n minus k. And we notice that there's actually a symmetry that occurs. This actually makes it easier to compute n choose k if we were trying to determine all the values of k. In addition, we also figured out a reasonable definition for when n is strictly less than k, what exactly n choose k would be. In that case, we noticed it was a 0, right? That's also a convenient thing for us to have. This brings me to now talking about something called Pascal's triangle. A neat mathematical structure. You can constructively build it to any size you like, but it's going to provide us a valuable relationship provides a valuable relationship in combinatorics. So you're going to find that this structure that we're going to talk about every once in a while just decides to spring up. And things that we discuss in one context may actually pop up within the context of this Pascal's triangle. So it's something that is worth knowing about. And it connects all sorts of different things, like number sequences, different properties that you may study in one context may actually appear in this structure called Pascal's triangle, which we're going to derive what that is here shortly. But namely, the way we're going to explore this topic is we're going to see and extend our ideas we talked about before. You know how we varied k in our computation of n choose k? Let's vary n. Let's increase values of n successively and see what happens. So what I'm going to do is I'm going to imagine I give you a set of size n. I'm not going to care so much about what the elements are in the set, as long as it's size n. And I'm going to imagine I want to consider all the subsets of size k for this set of size n. So all sorts of things pop up in this so-called Pascal's triangle. So I'm not going to focus so much on that right now. Instead, I want us to go through the exercise of computing n choose k and let's see if we could see anything interesting that's happening. So I'm gonna vary n vertically. I'm gonna have 0, 1, 2, 3, 4, 5, and we're gonna just allow it to keep going. And I'm going to have k, which is going to be 0, 1, 2, 3, 4, and 5. And I'm going to allow this to keep going. So what we're going to do is we're going to build this table. I'm going to write a little bit smaller, but fortunately for us, that shouldn't be too much of an issue. Okay. So, first, let's figure out what 0, choose 0 is. Well, if it makes it a little easier to study what 0, choose 0 would be, what would it be if I have... So I have no elements, and I'm choosing none of them. But the thing is, there is a set with 0 elements. It's the empty set, right? If I choose none of them, what is that? Well, I'll let you think about it, but the point is there's only one of them. But notice now after this, then k is going to be greater than n, meaning that I'm trying to pick subsets that are bigger than the set itself, meaning it has more elements than the set itself. So all of these will have 0 in them, and so on. It'll just keep going with zeros after this. Likewise, because of this property as well, I can already tell you which ones are going to have zeros in them right away. So notice that 2 is greater than 1. 3 is greater than 2. See, 4 is greater than 3. And 5 is greater than 4. So you know all those are going to have zeros. In fact, this will continue going on forever in these rows of zeros. Next, let's talk about... So instead of going row by row, I'm going to go column by column at first, and see if you can see any easy ways, at least for the first 2 rows, I'm going to do this. So I'm going to have 1 choose 0, then I'll have 2 choose 0, 3 choose 0. So I'll do it with the first column because it's so dang easy. 4 choose 0, then I'll have 5 choose 0. So what should all of these be? Well, based on the same argument I gave you, okay, I choose none of them. But there's only one subset that has no elements in it, right? It's the empty set. There's only one of them. So all of these will be 1, right? So all of those are 1s. Naturally, you can use our property we just talked about to figure out what this would be. What's 1 choose 1? Well, I have 1 element. I want all the subsets of size 1. How many of them are there? Just 1, right? This is just n choose n. That's just 1. And you can do the same thing, right, for all of these. As soon as you get where you're actually just along the diagonal here, whenever you would have a, like 2 meets 2, that's just 2 choose 2, right? Right? 3 choose 3. It's just 1. You do the same thing here. 4 choose 4. That's just 1. We have 5 choose 5. That's just 1. Now, notice. Let's try to use the property we just talked about previously about how there's a symmetry that happens over the values of k. So whatever goes right about here in this row, this will be kind of like the mirror point. So there's 1 on this side, 1 on that side. Whatever's here is going to be where it differs, possibly. Likewise, in this row, it will be that everything will mirror like this. And likewise, something will similar happen over here where it'll mirror like this. So we actually don't have to compute all of the values very delicately. We could just take advantage of the property we just proved previously. So what's going to go right there? Well, that will be 2 choose 1, right? Well, what's 2 choose 1? That's just 2, right? If you're not sure about that, just pull out the definition for 2 choose 1. So I have 2 elements. I choose 1. So I have 2 elements. So for example, if the set had A and B in it, the subsets would be A and B. So those are my 2 subsets. And I can do the same thing actually in this entire row, sorry, this entire column, right? You can see that it's just me picking one off from each of the elements and putting its own subset, right? So 3 choose 1 would just be 3. 4 choose 1 would just be 4, right? 5 choose 1, that's just 5. Yeah, that's quite the abomination of a 5, okay? Just roll with it. Just roll with it. It's sort of melting there. It's like that look when you have something in the microwave a little too long. That's what happens. So now armed with the material that you do know, what can we fill in here? Well, we'll notice that there's this one here. Well, that's 3 choose 2. Well, what's 3 choose 3 minus 2? That's 3 choose 1, right? So that is just, so 3 choose 2. So remember, we know that, so just remember that we know that n choose k is equal to n choose n minus k, right? So that means that if I give you something like 3 choose 2, then that's the same as me saying 3 choose 3 minus 2, which is just 3 choose 1, right? We already computed that. So this is just 3 right here. As I suggested, we have sort of like this mirror point. Likewise, we can do the same thing over here, right? So so I got 4 choose 1. So I have 4 choose 4 minus 1 is 4 choose 3, right? So 4 choose 3 is going to be equal to 4, right? And you do the same thing here as well, right? You have 5 choose 4. Well, that's just 5, right? Now, let's figure out what's going on in here. Okay, 4 choose 2. Now this one, unfortunately, we can't just simply attack in this direct way, but we haven't really observed kind of the killer property of the configuration that we have set up here so far quite yet. If you've noticed anything interesting going on with this table, you might be able to guess quite quickly what's supposed to go right there, but I'm not going there quite yet. Remember, we're still getting ourselves familiar with this binomial coefficient. So let's try to compute out what 4 choose 2 is. 4 factorial over 2 factorial 4 minus 2 factorial, right? We actually computed this in a previous exercise. Right? Because it's just 4 times 3 factorial. But I can extend it even further. I'll go 4 times 3 times 2 factorial over 2 factorial, 2 factorial. So the 2 factorial, they go. Then I have 2 factorial that turns this into a 2 because 4 divided by 2 is just 2. So I have 3 times 2, which is just 6, right? 6. Interesting. Interesting. Now, let's figure out what this one is. If we could figure out what this one is, then we know the answer for this one based on that property right there. Remember, it just mirrors. Like this. So, let's figure out what 5 choose 2 is. 5 choose 2. 5 choose 2. Well, it's 5 factorial over 5 sorry, not 5 factorial, it's 2 factorial. 2 factorial, 5 minus 2 factorial. So it's 5 factorial, 3 factorial. So I'm going to have 5 times 4 times 3 factorial over 2 factorial times 3 factorial. The 3 factorials, they go away. 5 times 4 divided by 2, it becomes 5 times 2, which is just 10. So this just ends up being a 10. And by our reasoning that we gave previously, 5 choose 2 is equal to 5 choose 3, because it would just be 5 choose 5 minus 2, which is equal to 3 in that case. Because 5 minus 2 would be 3 here. So it's 5 choose 3. I uttered that a little bit strange at first, but it's 10. It's 10. Now. What I want to do is try to figure out a general pattern that's going on with this setup. So the first thing I need to acknowledge for you is what Pascal's triangle is. So let me just use a different color here. So this diagonal here and below, this, what I've just described here, and below, this is what Pascal's triangle is. It goes on indefinitely, downwards and to the right. But there's something interesting going on with this triangle. So I must stress that this is Pascal's triangle aligned to the left. Some people will just write Pascal's triangle like a like sort of a triangle, literally. So something like this. So sort of like this. So it'll be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, like this. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. And it keeps going on forever downwards to sufficient size that you would like. So sometimes people will just write Pascal's triangle out like that. There's lots of neat things about Pascal's triangle, but I want us to notice something that's really neat about this triangle. So I really want you to think carefully about this. Okay. Why would it be that the answer here is 2? Well, it's when I have n is 2 and I have k is 1, right? But do you notice anything? Now keep in mind, we haven't really answered why this would be the case. But do you notice something just peculiar about this? Do you notice that 1 is here, 1 is there, and that's a 2 there? And notice that 3, and there's a 3, and there's a 6 right here, right? Do you notice also that 6 and a 4 is right here, and then that's a 10 right there? You also notice that 4, even 4 and 6, that's 10. We got 4 and 1, that's a 5. Heck, even it works on our edge cases too. Like with 1 and a 0, there's a 1 right there. It even works in these edge cases, but most certainly we just care about when it's simply just a positive integer and another positive integer. So notice, for example, even in this edge case here, like 1, 0, 1, 1, 2, and 3, 1, 3, 4. Notice that it's really something interesting going on here, right? Do you see that all I have to do to compute any one of the cells that belongs to a positive integer? So you notice that if I go, say k is 1 or greater, or n is greater or equal to 1, I can compute any one of the cells that exists over here, because all of these are just 1, right? And it's just 1 and then a whole bunch of zeros, right? I can compute each one of these successive ones, and this isn't the right color. I need a red, and I'm losing markers. I'm losing markers, everybody. So please notice that I can, if I add the results in the immediate up to the left and the one directly above it, it equals whatever is in that spot. So notice that 3 is equal to 2 plus 1, right? Interesting, right? You do the same thing here. So it's 4 plus 1 is equal to 5. Interesting. Well, let's extend out our triangle now to try to figure out what's being written down here. So this will keep going until k, we have k is equal, so imagine I give you k and so I fix k, and then that means I have k minus 1. And then I'm going to have another column that's going to be for k. And keep in mind, it keeps going on forever like this. But I'm just going to imagine I have n and k, and I'm going to fix k, and I'm going to fix n. So I'm going to have n, and I'll have n plus 1. I'm just going to move our triangle over just ever so slightly, okay? So, now, what would go right here? This is n choose 0, right? That's n choose 0. This would be n choose 1. This would be n choose 2. This is n choose 3. N choose 4. N choose 5. And then I have n choose k minus 1. And I have n choose k right here, right? What would go in the n plus 1 row? This would be n plus 1, choose 0, n plus 1, choose 1, n plus 1, choose 2, n plus 1, choose 3, n plus 1, choose 4. Then we have n plus 1, choose 5. And keep in mind, we still have our dot, 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 right? This keeps going. And keep in mind, all of these will still have 0 in them. All of these are just zeros up above here. All of this is zeros. These are all just zeros, dot, dot, dot. Don't want to make them look like ones too much. All these are zeros. That's the point. Then, what if I cared about this particular cell? This one right here. What about this one right here? Well, this is K, column K, row n plus 1. If the relationship that we've noticed here in our, and keep in mind, we don't know this is a matter of fact yet, right? This is just a speculation that we have. We haven't proven this. But if I take our idea from here, what would this mean in terms of the notation that we've been using? Well, it says that if I add the cell's value directly above me and the cell up and to the left directly, I should get what's right here. That's what it says. Okay, so what should go right here then? Well, let's think about that. Well, either way, whatever is here, we know that this cell will be n plus 1, choose k, right? That's what this will have in it. So I want you now to think about what should go right as an equivalency right here. And this will give us what we call Pascal's formula. So you wonder what Pascal's triangle is? This is what Pascal's triangle is. It extends on forever like this, and it keeps going. But it's named after the mathematician Blaise Pascal. Did all sorts of interesting stuff in his life. A lot of neat mathematical concepts, including even calculators. So some early computational history can be associated with Blaise Pascal. So now, let's put this all together. So if ever you want to compute successive entries in Pascal's triangle, we can use what we're going to come up with next here, Pascal's formula. So here's a theorem for you. And it's going to be surprisingly easy to prove because we actually have a few different pieces from our previous study of combinatorics that we can use to help us with this, okay? Namely, the addition principle. If we can have that, then we're okay, and it's actually really easy to prove this. So we're going to be proving Pascal's formula. You can use Pascal's formula to compute successive entries for n and k that are greater or equal to 1. So all you have to do once you set up the initial column and row, you could just keep using Pascal's formula to fill in the rest of the rows and columns, okay? So you don't have to do a whole lot of extra work. So this is Pascal's formula. So here's the theorem. So if you understood the pattern that we're trying to get out of this, what this is saying is that we consider any k, which is a positive integer. Actually, we'll say for any n and k that are positive integers, where n is less than or equal to k. It's going to be important for us. Otherwise, you're just going to end up with some funky business that just involves those zeros. Keep in mind, our formula will work even on the edge cases, as we discussed previously. It's just that n and k have to be positive integers, and k is less than or equal to n. I'm just getting myself very excited here. So, anyways, consider any n and k that are positive integers, where k is less than or equal to n. Here's what Pascal's formula is. It's that n plus 1, choose k. Remember, that's the cell that we're interested in on our table over there, some arbitrary row and column. This will tell us, based on our intuition, keep in mind we still have to actually prove it, is that this is n choose k minus 1 plus n choose k. Remember, this is the one that is directly above, so this is the cell directly above the one that we're interested in, and this is the one that's up and to the left. So once you have that in place, you can compute successive cells of the table. So we're going to use a combinatorial argument to prove this, and it's going to be surprisingly simple. Because something that looks kind of daunting like this, it'll match quite interestingly in a combinatorial view of things. So you got to think about it in terms of sets and subsets. And what we're going to do is we're going to take advantage of the addition principle to do this. That actually, when we talk about our subsets, there's actually a special property that's going to exist from one row to the previous, like the one directly above it. There's going to be a very special relationship that exists there that we're going to exploit. So consider an arbitrary, so I'll say consider any set A with n plus 1 elements. And I'm just going to give those elements a name, where A is equal to A1, A2, all the way up to AN plus 1. Now, here's the killer observation. This is going to come back to our basic counting principles, is observe the following. Observe that any subset of A of size k either contains an plus 1 or not. Those are only two possibilities if I fix one of the elements. In this case, I'm going to use the last one. So it's either going to contain an plus 1 or it isn't. Right? Because those are the only two possibilities, right? So if I pick a subset of size k, remember, we're going to be considering the size of of a subset of size k for a set with n plus 1 elements. There's only two possibilities. It's either going to have n plus 1 in it or it isn't, right? It's only two choices here. And notice that they are not overlapping. They're disjoint. So if I were to count these subsets, there's going to be the ones that have an plus 1 in them, and then the ones that don't have them in them. So the total number will be this sum of those two. And that's how we're going to bring in the addition principle. So we have our first case. Our first case is when a subset contains an plus 1. Then, what can you say if a subset of size k has an plus 1 in it? Well, we fixed an plus 1 in that subset, so that's already been determined. How many other elements can there be in the subset? Well, there's k minus 1 other ones, right? And we have to pick those. So this is going to play a big role in this, and you're going to see it's going to match up quite nicely with something we're seeing up there in Pascal's formula. So watch this. Then k minus 1 elements of this subset are from the set A1, A2, all the way up to AN. So what would these subsets look like? Well, you're just going to imagine every single one of them. You imagine you buy a dozen eggs, but every one of the dozens actually has always a red egg in it. If I asked you how many eggs were not red, well, they're all going to be coming from whatever distribution of the other eggs came from. So we're going to care about those. So if I want to know how many of these subsets exist, it matters what happens with all these k minus 1 other elements, how they get picked. So any subset here can be obtained by including an plus 1. So just imagine you're like tacking this on. It's just like, just add a little post-it note. So you have your subset of size k minus 1 from this set, and then you just tack on an plus 1 like a post-it note. It's like, look, I did all the work of picking these k minus 1 elements. Oh, here's my post-it note. Okay, there's an plus 1. Good job, everybody. That's all we're doing here. Obtained by including an plus 1 with a selection of k minus 1 elements from the set A1 that contains elements A1, A2, A3, all the way up to AN, which has n elements, right? That has n elements. So a question, how many possible subsets are there then? So if all of them are just an plus 1 with that tacked on, it's entirely determined by all of the ones where I pick k minus 1, many of them from n elements. Does that look like something interesting to you? It's right here, right? It's just this. It's right there. Hence, there are n choose k minus 1 many such subsets. Many such subsets. Right? That counts for the first case. That means now all we have to do left is we consider all of the subsets that don't contain an plus 1. Because those are the only two possibilities. Either it contains an plus 1 or it doesn't. So let's head over here and let's take a look at the next case. Okay, now we got our second case. So let's get to the second case. So let's consider when a subset does not contain an plus 1. Well, if it doesn't contain it, then most certainly we're only considering how many elements then? of that set. N of them, not all n plus 1 of them, just n of them, right? But we have to choose k of them. So in this case, k elements are from the set A1, A2, all the way up to AN, right? Because it doesn't contain AN plus 1. So how many of those are there? Well, I'll give you a hint. Is that other part of the Pascal's formula? Well, if I have k elements, I'm choosing from a set with n elements. It's n choose what? N choose k. So there are n choose k possible subsets. Well, now, let's establish the left-hand side of Pascal's formula. Okay, we have n plus 1, gotta be careful here. We have n plus 1 many elements. We choose k of them, right? How many of those are there? How many of them are there? Well, that counts the two cases. Well, the number of subsets of A1, A2, all the way up to AN and AN plus 1, remember there's n plus 1 of them, of size k, by definition, is n plus 1 choose k, right? That's the left-hand side of the formula. But I've considered now how you could get all of these, right? And how many there are. Therefore, by the addition principle, remember, we have the subsets that contain AN plus 1 and the subsets that do not contain AN plus 1. We figured out how many of those there are. That's all the possible subsets, right? All the subsets of size k from the n plus 1 elements. But we determined those counts, and that would be all of those subsets. But we know it's equal to this, and we're done. So we have, therefore, by the addition principle, n plus 1 choose k is equal to n choose k minus 1 plus n choose k. And we're done. That completes the proof. So indeed, Pascal's formula is correct. And as I mentioned, you can use Pascal's formula to compute successive entries in the table. For those that maybe know a little bit more about algorithms, you might think about this carefully. You may have heard of a concept called dynamic programming. In dynamic programming, you build answers by successively combining them. Usually it's in the context of optimization problems. But you can imagine, I want to compute the answer of a given cell. Well, the answer of the cell is always the one directly above it and the one up to the left. So you can always build n choose k for positive integers n and k, where k is less than or equal to n, using this formula. And you can build it in a completely bottom-up fashion like this. So if you ever find yourself curious about like building a table of these, that's one way you can calculate it fairly quickly, using some of the other rules that I talked about here. I'll let you think more about what that table would represent in terms of subsets. So are there any questions? Any questions? So we talked about Pascal's formula. After this, we're going to talk more about properties that Pascal's formula actually has. So So I'm just going to erase the board here, and I'm going to put back up Pascal's triangle, but I'll draw it without the big fancy table. Instead, I'll I will use kind of like the fun picture, the one that doesn't look just like a table. It looks more like a triangle. We'll talk about some properties it has. So let me just write it up again. We're going to use this picture to help us. So I'm going to use, so I'll have 1, 1. Actually, I'm going to start at the bottom and work my way up. 1, 5, 10, 10, 5, 1. Keep in mind, it keeps going downwards. I have 1, 4, 6, 4, 1. Then I have 1, 3, 3, 1. Then I have 1, 2, 1. Wow. I did a surprisingly good job placing those ones up there. It's almost like I've done this many times before. But we're going to see some fun properties that Pascal's triangle actually has. Some of them I'm not going to go into deep details about here. But if you're curious more about it, let me know in the comments or in the chat, and I can prepare a proof containing that claim in the future. And maybe I could do a lesson video that includes that as well, or maybe cover it in a future live lecture. Either way, I'm happy to answer any questions. And if I don't know the answer, because keep in mind, Pascal's triangle's got all sorts of wacky things that people might call black magic, but it isn't in it. So I'm going to highlight a few neat properties that Pascal's triangle has. I'm just trying to look carefully a little ahead so that way I'm not going too off the path, because this is one of those rabbit hole topics that you could just keep going on as long as you like about it, and it just kind of keeps going. I don't want to give you too much at once. I'm just going to move this over here. We don't need this over here. Okay. Just getting myself quite excited about this. I have a lot more pictures this time around, so that's why I'm looking a little more carefully at my notes. Like again, I usually use the notes as a prop to help us guide things, because sometimes there's a very delicate thing I need to make sure I cover properly. Sometimes I just do it off the top of my head. Sometimes I write it down. It's just sort of one of those things you do when you get a very good hook over how to lecture people on things. Some people just never get that skill. Some people do. It's something that's just sort of a fun thing. Either way, we're having ourselves a blast. But anyways, let's get back to where we were before. So previously we talked about Pascal's triangle, this construction that involves our k combinations, and and the way we came up with Pascal's triangle is we enumerated over values of k and n choose k, and we noticed a property that allowed us to compute successive values in Pascal's triangle called Pascal's formula, and we proved that that formula can indeed be used to compute successive row entries in the triangle. So just for context, I drew the triangle here, not left aligned. It'll be a helpful aid for discussion here. So we're going to talk about some properties. By no means is this a complete list. We're going to talk about some properties of Pascal's triangle. And if you're curious more about some of these more delicate details, let me know. Let's talk about some properties of Pascal's triangle. So the first thing I want to point out is I alluded to this idea that there's a lot of combinatorial properties that exist in Pascal's triangle. That shouldn't be very much of a surprise so far. You may be staring at this and you might see some interesting things already. But I'm going to start at some simpler, more direct relationships, then we'll kind of dig in a little further. So I'll also derive and convince you that one of these actually isn't nothing to do with black magic or anything like that. It makes complete sense if we use Pascal's formula. So we're going to highlight some. So highlighting a few properties Pascal's triangle has many. I know it sounds a little funny. I'm just getting really excited here. So highlighting a few properties, Pascal's triangle has many. So for example, many number sequences appear in it. So just as an example, so I'm going to give you these examples, and then we're going to see where they are in the triangle, okay? So while I'm telling you about the number sequences, see if you could find them in this triangle. They actually can appear in several different ways. I'll just highlight one way they can. So they can appear in many different ways. This has to do with several factors, such as the symmetry along the triangle when you read it from like this direction or from this direction, and there's a few other ways as well. So, for example, you can consider the positive integers. So 1, 2, 3, 4, 5. So where are the positive integers in here? So there's at least one way you could find them, right? There's at least one way you can find them. So you might see them right here. Right there. Or you might see them like this too. There's your positive integers right there. Let's consider another example. Let's consider the triangular numbers. Some people call them just triangle numbers. So if you've never heard of the triangle or triangular numbers, this is just each term is the sum of the numbers up to that term. So for example, the first triangular number is 1. The next one is 3 because this is 1 plus 2. The next one would be 1 plus 2 plus 3, which is 6. The next term would be 1 plus 2 plus 3 plus 4. So just, you got to look at it like it's the next level above this in terms of adding the terms. What's 1 plus 2 plus 3 plus 4? That's 10, right? Okay. What's for the fifth term? It should be 1 plus 2 plus 3 plus 4 plus 5. That is 15 because it's just simply this plus the next term. Then you can keep doing this forever. So the reason why they call triangular numbers, I'm not going to focus so much about this here. So you can imagine I write out a triangle like this successively like this and ask how many of these balls or dots exist for each successive triangle based on how many rows I include in the triangle. So notice this has 3, third one has 6, fourth one has how many? 10. And you keep this process going. So where are the triangular numbers? Let's keep it to the same orientation I did before. It's directly below the positive integers. Right here. So there's your triangle or triangular numbers. Okay. I'll even throw another number sequence in here. There's even more. I want to stress this is not a complete list by any means. So here's another example. So there's what we call tetrahedral numbers. And it has a very similar relationship to the above two sequences. So this one is where you take each term of the triangular numbers and you successively add the first I of them. So the first term is 1. The next term would be the sum of the first two triangular numbers, 4. The next term, the third term, would be the sum of the first 3 triangular numbers. So in this case, it should be 10. Then the next term of the tetrahedral numbers should be the first 4 triangular numbers summed up. So notice that this will be 1 plus 3, that's 4, plus 6, that's 10, plus 10, that's 20. And you can do the next one, it's 35. Where are those? Well, you see 1, 4, 10, and then we'll go 20 and keeps going down like this. So there's your tetrahedral numbers right there. You might guess quite quickly that this has something to do a little bit with geometry, but I'm not going to highlight that right here. So there's your tetrahedral numbers right there. So there's a whole bunch of number sequences that pop up in this thing. These by no means are the only ones. But you might look at this and say, Dan, why would the triangular numbers pop up in here? Is this some spooky stuff that I should watch out for? Is this some black magic? So I assure you this isn't some sort of like splay tree or something. That's a joke, by the way, just to be clear. It's actually because we can actually show that this is indeed going to be what happens in Pascal's triangle. So why don't we try to derive a reason for why this would be the case? So I want you to look carefully at where the triangle numbers begin and why would they start appearing there. So why do the triangle or triangular numbers why do they appear in here? So just for context, if you're wondering how you determine the ith term of the triangular numbers, it would have a form that looks like this. You might recognize this as the closed form for the arithmetic series. So it's going to have a form that looks like that. So why would it pop up in here? So why does it appear in there? So notice, so I want you to look carefully at that triangle. Remember, as we do this, so each one of these successively is going to end up being different values of k. So this is what k is 1, this is k is 2, this is when, this is k is 0, that's k is 1, k is 2. So notice this is when k would be 2. If you're not convinced by this, please look back at our table we computed when we were deriving Pascal's triangle. So this would be the row for when n is equal to what? Well, let me lay out the condition. So please, let's take a look. So notice every position, a triangular number appears. I might call them just triangle numbers for brief if it makes it a little bit too much. Notice every position a triangular number appears is whenever k is equal to what? So this is k is 0, k is 1, k is 2. Whenever k is equal to 2. Specifically, this happens when if n plus 1 is greater or equal to 2. Then I get each successive triangle number from there. So it's going to make it a little easier for us to work with if we notice that we can get each successive one if this is satisfied. So if you aren't seeing it right away, it's just the same as me writing n is greater or equal to 1. So if I subtract 1 for both of these. This is just to make it so it's a little easier for me to compute each successive triangle number. So you're going to see that I'm going to find some way of getting each successive triangle number from a previous one. In some way. Well, what does that mean? So each row, I should say successive row, corresponds to a value for n plus 1. So let us compute n plus 1, choose 2, because that's what k is. Each successive triangle number will appear the one next to it, right? So I want to do something with the triangle to know each successive one. So let's do this. Well, we can use Pascal's formula. Well, by Pascal's formula, well, let's see what happens. So I have n plus 1, choose 2. Pascal's formula tells us this is n choose 1 plus n choose 2, right? That's what Pascal's formula would tell us this is. Well, n choose 1 is easy. That's just n, right? And then n choose 2 is n factorial over 2 factorial times n minus 2 factorial, right? Well, just to make this a little easier to work with, I'm just going to write this out a little bit more carefully. Well, this is n plus n times n minus 1 times n minus 2 factorial, right? 2 factorial n minus 2 factorial. Well, the n minus 2 factorials cancel each other out there, and I end up with something that will look like n plus n times n minus 1 over 2. I'm just going to bring this all under a common fraction or common denominator. So that means I'm going to have 2 n's over 2, because that's equal to n. So I'll have 2n plus n times n minus 1 all over 2. Let's expand the second term. This is just 2n plus n squared minus n over 2. Well, what's that? Well, I have 2n minus n, so it's just n, right? Well, that's just, well, it's not that we don't have a 2n anymore, we just have n, right? So it's n squared plus n divided by 2. But what's this? What's this? Let me factor it so it looks a little nicer like that thing I have over there. Well, it's n times n plus 1 over 2. Boom. There's the general, that's the general term for the triangle numbers, right? And that it's not a coincidence. It appears in Pascal's triangle. It's not, no black magic here. It's not just the coincidence. It just appears in that construction for this good reason. It always will have that form. So, interesting stuff. So different number sequences can appear directly in the triangle. That's the first thing. The next thing is that you can go even further. There's sometimes properties where the triangle actually has hiding in it through successive operations, such as adding over parts of the triangle, different things. So let's head back over here. So I'm just going to say that these numbers are not black magic. These are not black magic. No. It's not black magic. Right, my little friend? It's not black magic. I'm not getting any answers, okay? So, they're not black magic. But you could actually find other reasons why other things appear as well. So let me show you another peculiar one. But it is surprisingly neat. So watch this. So what I'm going to do next is I'm going to show you that there's these shallow diagonals that exist in Pascal's triangle. Now, if you don't like the way I'm doing this with just this triangle, just look at the diagonals in our table when we computed Pascal's triangle previously. So let me do this carefully. It requires some artistry to get this right. So anyways, so I'm going to do some shallow diagonals. So I want you to notice something. It's interesting is happening. It's those two. Yeah, we're doing good. We're doing good so far. Sorry, this takes a lot of patience. It's just drawing lines. Okay. I want you to notice something. Add the numbers that appear on each one of the red lines. So each one I crossed over. So I have 1, then I have a 1, right? 1, 1. This has 2. This one has 3. If I add up, 1 plus 2 is 3. 1 plus 3 plus 1, that is 5, right? 1 plus 4 plus 3, that is 8. And you can keep making shallow diagonals like this. Does anybody recognize that number sequence that I have written up there? And keep in mind, this keeps going on. Like, you keep this pattern going. Does anybody recognize that number sequence? What is that number sequence? So others appear too. So just as an example, you might know about the Fibonacci numbers. So the Fibonacci numbers are defined as follows. So I'm just going to define it like this. Fib of n is going to be equal to it's the previous term plus the term just before that one, 2. So fib of n minus 1 plus fib of n minus 2. Or suppose that you define fib of 1 to be equal to 1 and fib of 2 to be equal to 1. So if you notice this, it means that each term is the sum of the 2 previous terms. So I have 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. And you can keep going this. So summing the shallow diagonals produces the Fibonacci sequence. So that's interesting, right? Now, there is a good reason for that. You can actually prove, if you formalize what these shallow diagonals are carefully, you could prove using mathematical induction this is in fact the case. Now, let me show you another property. So that's one way you can add things in Pascal's triangle. You can also find some other ones as well. So I want to show you another way you can add some across the table. So I'm going to use a blue marker. I'm going to draw in some more lines. I'm really ruining this picture. But the point I'm getting at is that there's a lot of things going on with this triangle. So I'm going to put some lines through each row. So what does this row add up to? If I look at the numbers in that row, it's 1. How much does this add up to? 2. How much does this add up to? 1 plus 2 plus 1. So 1 plus 2 plus 1, that's 4. 1 plus 3 is 4. 3 plus 1 is 4, so this is 8. 1 plus 4, that's 5. 4 plus 1, that's 5. 6 plus 10 is 16. And you can do the same thing here. We got 20. We got 30 and 32. What's going on these rows? What are those? What are those? What's happening on the rows if I sum up across the rows? So each sum of a row equals a power of 2. So notice that 1 is equal to the power of 0. 2 is equal to the power of 1. 4 is 2 squared. 8 is 2 cubed. 16 is 2 to the power of 4. And 32 is 2 to the power of 5. And you might ask, Dan, why is that true? Well, there's something rather interesting if you think about it. This is actually just a summing across all values of k and choose k, right? Because each row is a value of n. And the values here, these are all the ones where k is less than or equal to n, right? So whatever the result of the sum would be the sum of all the values of k for a given n of n choose k. And whatever that is, the claim here is that that's equal to a power of 2. Now, I'm not going to prove that here, but we're going to actually implicitly prove this when we study something called the binomial theorem. So the binomial theorem actually gives us the answer to why this happens. So the binomial theorem actually gives us the answer of why the second one occurs. And we'll be exploring that next. Wild stuff, right? Are there any questions? Any questions at all? So those are some properties of Pascal's triangle. There's a lot of them. These are just a very small subset of them. So I want you to think about these triangular or triangle numbers. So please think about those and ask yourself if that makes sense. It's just, remember, the way I formalized it here is I wanted to use Pascal's formula. So what I did is I went down one row. And I must stress that you can do this, presuming you fill in the zeros. But the thing is, I would like to have it where I could get each successive term. So you'll notice that the way I did that was I just went one row down, and that's how I got n plus 1 choose 2. So I just make sure that the n plus 1 is there such that I have 2 terms directly above it that are within the triangle. So let me just erase the board here. If any has any questions, please ask. I'm happy to answer them. The next topic we're going to talk about here is the binomial theorem. It's the last one we're going to focus on today. So the binomial theorem actually is something that you may have learned in high school or secondary school, but you may have learned it just sort of at a surface level. So we're going to go much deeper about what the binomial theorem is. And I might teach you a few rules that you may have learned in grade school and where they come from. So depending on how good your teacher was, you may have learned some of these things before. I don't consider this next topic rather advanced, but most certainly it's got a lot of little intricacies to it that make it interesting from a combinatoric standpoint. So if you've ever heard of binomials or monomials, or trinomials, you might have heard about some of these things. that are coming up next. So this is more of an algebra example, but most certainly it has strange implications for some of the things we actually just discussed here too. But it also spits out general forms for multiplying binomials. Which makes it interesting from an algebraic standpoint, but also has some neat combinatorial properties that are hiding underneath it. I'm just going to grab this marker here. There we go. Not sure how good this marker is. Let's see the disaster this is. Surprisingly, it's very nice. I'm going to use it. Cross our fingers, it's not going to trick me. If a marker had the ability to trick someone. I'm just joking around, of course. Let's see here. Next we're going to be talking about binomial theorem. And then when we're done talking about the binomial theorem, I'll open up the floor to any questions. If anyone has any questions. I'm happy to answer those. So again, if you're enjoying the content, whether you're watching this now live or watching this in the future, please tell your friends to come join the fun. Everybody is welcome here. We have ourselves a blast. I'm just figuring out which things I would like to move over for us. That way, because I have some fun things for our demonstrations here. Okay, I think we're doing pretty good. We're actually doing pretty good on time thinking about it. Okay. Let's get in on this. I'm just going to drink a little bit of water here. My apologies. Okay. Let's get into this. So previously we had talked about Pascal's triangle, and we had noticed that there's this neat property that happens with Pascal's triangle, namely that we had this summing of the rows, and each row would sum to a power of 2. I would like to be able to try to answer that question of what's going on there. Now, to answer that one, including other questions, I'm going to address something from algebra, referred to as the binomial theorem. So let's talk about the binomial theorem. So we're going to talk a little bit about algebra first, and then we'll kind of eventually work our way back to answering that question about how do we know that the sum of each row of Pascal's triangle is indeed a power of 2. So just some background. A common form in algebra is the binomial. So you might ask, Dan, what the heck is a binomial? So let's talk about that. So a binomial is a sum of 2 terms, usually numbers. For us, this will be a plus b, where a and b are numbers. So I'm going to start off by exploring a question about powers of binomials. So meaning how many times you multiply a binomial. I want to explore this question, see if we can pull out from it some combinatorial structure that's happening underneath the hood. So that's going to be our main goal. So for any non-negative integer n, what is a plus b to the power of n? So let's explore this for some values of n. I'm hoping that we can talk a little bit about how you can figure out which one is and what it isn't. And we're going to re-explore some topics you may have seen possibly before. So first, let's consider when n is equal to 0. Let's start off with that. Well, a plus b to the power of 0. You know, anything that you add where it's a plus b and these are numbers, you raise that to a power of 0. What is that? Well, that's just 1, right? We have n is equal to 1. Well, a plus b to the power of 1, well, that's just simply a plus b, right? That's just the thing. A plus b. How about n is equal to 2? Now, I want to re-explore something. You may or may not have heard of this before. You may have learned it in grade school, possibly. It's a helpful way of remembering how to multiply binomials. So just think of this first as an aside, and then we'll work to answering this question. So first, in grade school, maybe, maybe not. I'll say maybe, question mark. You may have learned a rule called the FOIL method. So if you're wondering what the FOIL method is, what it stands for is as follows. So it means first, outer or outside, depends on who you talk to. Inner, inside, and the last one's last. So this gives you a simple way of remembering how to multiply binomials. But honestly, I'm going to show you that you don't need to remember such silly rules like this, although they do work, but you don't have to remember it like that. It's actually a much more general way of just viewing the same thing. It's just meant to be a simple way of remembering what you're doing. But I find a lot of time when they teach you this, they don't tell you why it's the case. So let's talk about this. For multiplying binomials. And is applied as follows. So suppose that I have numbers a1, b1, a2, and b2. So if I give you a1 plus b1 times a2 plus b2, you may have learned this to go like this. You multiply the first of each, that's the f, a1, a2, so this is the first, that's your f right there. Then you have a1, so it says now you're going to go outer, so we have a1 times a b2. There's your O part. Then next, you have the inner part. You have b1, a2. You take the two inner terms, b1, a2. So this is the I part. And the last, we just take the last two like this. b1, b2. So there's your L right there. So that's how you would apply using FOIL. Now, you might say, Dan, why would this work? And why does this, why? Like this is how I learned how to multiply binomials. We never really were ever explained by our teacher why this works. So let me just show you, just for context, what's actually going on. Or at least this is one way of deriving it. So really, actually what's happening is we're actually taking advantage of distributive properties of numbers over multiplication. That's actually what's happening. At least that's one explanation I could provide for you. So really, so what's actually happening? So what's actually happening? So let's revisit really what's going on here. So what's actually happening? Well, we are multiplying each term in the first pair, so the binomial in the first binomial, in the first pair, or binomial, I'll say just binomial to keep it simple, first binomial, against each term in the second binomial. Each term in the second binomial. And adding these products. So just to really explain or hammer this in where the heck this came from, let me do it with just A and B. Just A and B, because this is more what we're interested in. So for example, if A1 equals A2 is equal to A, and B1 is equal to B2 is equal to B, then if I give you A plus B times A plus B, I want you to look at this as just one variable, okay? I want you to just look at it just as one variable. So imagine this was just like X or something. So imagine this is just to make it look a little scary, well, a little less scary, sorry. Just imagine this is just like X. What would you do in that scenario? You would distribute X across A plus B, right? So you would have XA plus XB, right? So the same thing happens here. There's no black magic happening. So I'm just distributing over one of the binomials. That's all that's actually happening. So this is A times this. So I take A times this, B times this. I'm distributing A plus B, this binomial, over each one of these terms. So I have A times A plus B times A plus B, right? That's all that's happening. So I take this, multiply it by A plus B. Take B, multiply it by A plus B, right? That's all that's happening. There's nothing to memorize here. Just remember, the multiplication is distributive like this. So now, what do you end up with? A. So this is A times A is A. Then I have A times B. So I have A, B, plus B times A, plus B times B. Look, there's your FOIL right there. Do you see it now? So if you're not seeing it right away, go back to the other example. Just put A1, A2, B1, B2 in, and just go through the same exercise we just did here. So the point, I'm just going to keep it explicitly like this. It's going to be helpful for us to exploit or discover the underlying structure of what's happening when we multiply binomials. Is first, notice that I had multiplied A plus B twice. That's the first thing I want you to notice. So notice that each one of these has either an A or a B, and there's two of them in each one. Each of these products has two variables, right? A or B, right? So now, if we understand how that works, let's try n is equal to 3. So let's do n is equal to 3. So all I'm going to do is I'm going to use n is equal to 2 to help us do n is equal to 3. So let us expand on the previous case. So if I have a plus b cubed, I have a plus b cubed. Well, what is this? Well, if I know the answer to a plus b squared, which is this, how do I get a plus b cubed? I just multiply it by a plus b. And you'll notice that since I have the answer to a plus b squared, it's sitting right here, what can I do with this? Do the same exact thing. I distribute across each one of the terms that is the result of a plus b squared. I multiply each one of these with this binomial. So this is the same as me writing AA plus AB plus BA plus BB times A plus B. Then I'm going to now distribute it across each one of the terms, the resulting products. So that's right, B plus A. I want to keep it simple. A plus B. Then I got the third term, BA times A plus B. And I have BB times A plus B. Next. Now I gotta multiply this all out, okay? So let's do this. So I have AAA, right? AAA. Then I have the other possibility. So thinking about it as an either or is rather helpful for us in this discussion. So I have AAA, then I have AAB plus ABA plus ABB. Then I have BAA. That BAB plus BBA plus BBB. And now if you simplify this, that will give you, so if you take all the like terms and you lump it all together, you'll end up with an answer for n is equal to 3. But I'm going to explicitly keep them in this form, okay? Just to make it easier for you to see what's happening. So again, notice n is equal to 3. Each one of our terms, each resulting product, has 3 variables in it. And each one is either an A or a B. So take notice that I can uniquely determine each one of these. So notice that I can either pick an A or a B. And each one of them has either an A or a B in the first spot, an A or B in the second spot, and an A or a B in the third spot. I'll let you check that. So next, let me define a few terms. So let's head over here. Now let's proceed. I'm gonna dance on over. So let's talk about what a factor is. So the number of factors. So I'm going to use this term factors. You might know of this term from factoring. Number of factors of a binomial is the number of binomials rewrite it in a write out in a product. So the number of factors of a binomial is the number of binomials we write out in a product. So for example, if I did a plus b to the power of 4, it has 4 factors. We have a plus b, a plus b, a plus b, and a plus b. We would call this factor 1, or the first factor. We can call this factor 2, or the second factor. This could be factor 3. And this is factor 4, or the fourth factor. So, as I mentioned to you, we can completely determine any one term that appears in the expansion of this product, just like in our n is equal to 3 case. So we can completely, so this is going to be rather important for us. So please take note of this. We can completely determine any one term that appears in the expansion of products. So remember, we end up with just we're summing a bunch of products, right? That appears in the expansion of products for, suppose if we considered n is equal to 4, we would have a plus b to the power 4, just as an example. Through selecting either a or b for each A or B from each factor. So what I'm saying is, if I were to give you A, that if I pick this A from the first factor, and I pick an A from the second factor, and I pick an A from the third factor, and I pick a A from the fourth factor, this will exist in the list of terms, the products that would appear in the sum that equals A plus B to the power 4. That's what I'm saying to you. So let me just give you an example. So just as an example, if I consider a plus b to the power 4, well, this is just like I did before, is a plus b cubed times a plus b. Well, I already know the answer to this. So this is just AAA plus AAB plus ABA plus ABB plus BAA plus BAB plus BBA plus BBB. I'm trying to do that without breathing. It takes some practice, okay? And then I multiply this by a plus b. So remember, this is the product of 3 factors, right? So this is all the products with 3 factors. Then all we're doing is we're appending an A or B. That's the kind of combinatorial mindset I really want you to look at when we're looking at this. Is I have the result of 3 factors being multiplied out, and then I append either an A or B. So you can even look at this, they look sort of like strings when I could just append an A or a B. But remember, algebra has all sorts of fun other properties, so we got to be careful when we say things like that. So this is just AAA plus AAAB plus AABA. So remember, all I'm doing is I'm going through each one of these terms. I write an A after it, or I write a B. So I go through each one of these. I'm just A. Then the next one would be AABB. So now I've considered AAB. So now let's do ABA. ABAA plus ABAB, right? And then next we've got, so far, it makes it a little easier to help us maybe keep track of these. So we got ABA, I got ABB next. So we got ABBA, got some ABBA. And then we got ABBB. Now we got all the ones with B's. We've got BAAA plus BAAB plus BABA. We got Baba. I think I got Grandma. Got BABB plus B. Let's go with B. I think it's BB. Yeah, because the next one is BBA. So we got BBAA plus BBAB, right? And then last, we have the last 2. Then we have BBBA plus BBBB. So now, do you notice that I can just simply pick a selection of A's or B's? So either A or B. You can imagine each factor like a position. If you think about like a position, this all clicks really nicely. So if I pick an A, then a B, then a B. You'll see it's in this list of terms. So each of these products actually can be completely determined by the choices of either A or B for each factor. That's the claim. And you can see it right here, right? You can do this with any one of these. So just like we see with the previous ones, you can keep doing this. Like if I encourage you, if you're not convinced by this, try a plus b to the 5. Now, what I'm going to do next is I'm going to take this term, this collection of terms right here, these resulting products, I'm going to now notice something. Because algebra has more properties than just saying, oh, well, look, I can write these out nicely, right? You know, we can actually group like terms, right? We can take terms that are similar. We can commute elements in products. We can take like terms, so we can associate them differently. So why don't we do that now? So I'm going to take what I have, that list over there. Now I'm going to simplify it down, and we'll see if we see anything interesting pop up. And please take note of the fact that in this example, n is equal to 4. So I want you to think back, just think back to Pascal's triangle. If you could think about Pascal's triangle. So notice by associative and commutative laws, laws of algebra, some terms are the same. They're like terms. So we're going to group them together. And I can actually group them into 5 distinct categories. So the first category is those that have 4 A's in them and no B's. They always look like this. So they have 4 A's in them, no B's. So there's one of these. So there's one many of those. The next one is when I have 3 A's and 1 B. So remember, like I said, I can rearrange some of these. So for example, notice that I have 2 B's in this one and 2 A's. This one also has 2 B's and 2 A's in it. So these are actually both the same. They have the same result, algebraically speaking. So let me just list out these for when I have 3 A's and 1 B. So that was the case when I had 2 A's and 2 B's. That'll appear actually in a list of those that I'll get to in case 3. So I'll have AA, AB, then I have AABA, then I have ABAA, and then I have BAAA. So there's 4 of these. There's 4 many of those. Next, let's consider when we have 2 A's, 2 B's. Well, we're going to have 2 of the ones I just mentioned. We'll have AA, BB. We're going to have AB, AB, ABBA. So I'm just grabbing all the ones with 2 A's and 2 B's in it, and I'm just listing them out for you so that way you can see how many of them there are. So I have ABBA, then I have BAAB, then I have BABA, got the babushka, and BBAA. So that has 6 many, right? There's 6 there. 1, 2, 3, 4, 5, 6. There's 6 of them. So next, let's boogie on here. Let's do case 4. So now I have 2 1s, 3 B's. So I have A, B, 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 A, B, 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 A, B. And then I lastly have B, 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 A. So notice I've just simply considered each case where I just put A in different spots among the 4 positions. You'll notice that actually when I write it out like this, it should remind you a lot if I was asking how many strings there are that have that many symbols in those spots. So it should remind you a lot of the earlier counting principles that we're looking at. except we're mapping them onto positions. So in those exercises, that exactly is what we did. Then lastly, we have it where we have, wait, did I, oh, that should be 1. For some reason I wrote 2 there. I didn't have Miss Kitty or anybody to tell me, don't do that, Dad. You've gone too far, you put a 2 there. It's too late now. Now I fixed it though. All that Miss Kitty, I don't know where she's at. So so let's consider we have no A's, 4 B's. So this is easy, it's just 4 B's like this. Well, there's 1 of those, right? So now what I want to do is, I know how many of these are each. 1, 4, 6, 4, 1. That should look oddly suspicious to you, right? I want you to think to the 4th row, so when n is equal to 4, actually specifically I want you to think of when n is equal to 4 in Pascal's triangle. What were the binomial coefficients that you read in that row? 1, 4, 6, 4, 1. When n is equal to 4. So I should be careful. Depends on where you count the rows are from. It's when n is equal to 4. So when we combine like terms, then a plus b to the power of 4 is equal to 4 choose 0, a to the power of 4, b to the power of 0, plus 4 choose 1, times a to the power of 3, b to the power of 1, plus 4 choose 2, a squared, b squared, plus 4 choose 3, a to the power of 1, b to the power of 3, and lastly we have 4 choose 4, of a to the power of 0, b to the power of 4. But what is that? What is that? No period, no period. I'm going to simplify it further. Well, what is that? Well, let's see. Well, this is just, remember, that's just 1, so it's just a to the power of 4, right? So I'm going to simplify this. Got 4 times a cubed times b plus 6 times a squared b squared plus 4ab, so 4ab cubed, where b is cubed specifically, plus b to the power of 4. So all I've done is notice the coefficients, they match that row of Pascal's triangle. So there's your binomial coefficients, and you end up with this form right here. So for example, I encourage you to try going through the same exercise we did here with n is equal to 3 or n is equal to 2, and see if you could come up with the binomials, specifically when n is equal to 2, see if you end up with exactly what you would anticipate if you expanded if you took those terms and you simplified it. Do you see if it matches up exactly with what you'd get from, say, the FOIL method? So you notice that this actually gives you a generalized pattern if you think more about it. So the idea more generally is the binomial theorem. So here's the binomial theorem. So we're going to prove this now. So you'll notice the big part about this is that the numbers themselves didn't matter a whole lot in this process, right? So I'm just going to presume that they're just real numbers. So they didn't really matter. All that mattered for us were the rules of the algebra. The fact that we can do that with those terms. Perhaps there's some algebra where it doesn't have commutative and associative rules like that. But I'll let you think about that. But the point I'm getting at is that for real numbers, we can think of A and B as just numbers, right? In the sense that we're talking about. They could be fractional numbers, it could be whole numbers. It doesn't matter. They're just numbers as far as I'm concerned in our discussion here. As long as they have the properties that allow us to identify the structure that we're going to use here. So we're going to prove the binomial theorem, which characterizes a row. Like you can see that hiding in it is a row of Pascal's triangle. So we're going to use that fact after to actually answer the question about why the sum of each row of Pascal's triangle is a power of 2. Once we have the binomial theorem, we'll be able to answer that. So after this, I will talk about that. So I'll specifically talk about it after we use the theorem so you can get used to it. It's a valuable theorem to be aware of. You want to remember the form of what a binomial would be. This theorem is your best friend. For any a, b, which are real numbers, I'll let us use real numbers here, and n, which is going to be a non-negative integer. I must stress that there do exist other forms of this theorem, but ours, we're just going to presume the exponent is a non-negative integer, so it's allowed to be 0 or above. What a binomial theorem says is that a plus b to the power of n is the sum from k is equal to 0 to n of n choose k times a to the power of n minus k multiplied by b to the power of k. So this is the binomial theorem. So there's a few things I really want to point out is notice that how I showed you from case by case, it alternates on, so this goes down, this one goes up on k, and each one has the binomial coefficient as we discussed previously. So if you're looking at this and like, oh, what the heck does that mean? Try it with n is equal to 2 and see if it matches exactly what you'd expect a binomial to be if I took a plus b times a plus b and simplified. So to do this proof, we're going to break it into 2 cases just because the argument is easier when I can presume that n is greater than 0. So I'm going to break it into 2 cases. The first case is really easy. So I'm just going to prove the claim directly for n is equal to 0. Then when n is equal to 1, 2, 3, or higher, I'm going to use a combinatorial argument. I must stress that if you don't like this argument, you're welcome to prove it algebraically. Or within, I believe the standard proof for this is actually induction, actually. Yeah, it's induction, sorry. Yeah, you can use induction if you don't like this combinatorial argument. So, here we go. So, we consider 2 cases. First, when n is equal to 0, and when n is greater than 0. So the first case, we're just going to assume n is equal to 0, and we're just going to prove it directly. And of course, these are all values of n, and in each one of the cases, it won't matter. We have to argue regardless of a or b that the claim is true. So when n is equal to 0, the left-hand side, what's the left-hand side say when it's 0? Well, we already established it's just 1, right? The left-hand side is a plus b to the power of 0, which is equal to 1. Regardless of a or b, so whatever a and b's values might be, when n is equal to 0, the right-hand side is as follows. So let's take a look at what the right-hand side says. The right-hand side, we're going to plug in when n is equal to 0. The right-hand side is as follows. The sum from k is equal to 0 to 0 of 0 choose k times a to the power of 0 minus k times b to the power of k. Remember, I just put 0 everywhere where n was. So then, remember, sum from 0 to 0, well, I'm just going to have a single term in here. It's just 0 choose 0 times a to the power of 0, b to the power of 0, right? Because k only is allowed to be the value 0. Well, 0 choose 0 is just 1, right? A to the 0 is 1, b to the 0 is 1, so this is all 1. So the claim holds. So the claim holds for n is equal to 0, right? So it holds for n is equal to 0. Now we got to consider when n is greater than 0. So our second case is when n is greater than 0. So we're going to start by considering the left-hand side and see what that means based on a discussion about factors. So consider the left-hand side, which is a plus b written exactly n times, right? It looks like this. A plus b to the power of n is equal to a plus b, and so on, a plus b, but this is written n times. Now, when we take this, as we discussed previously, we can take the resultant of this and we result with an expansion with a whole bunch of products. What did we say about those products? How many variables appeared in each one of the products? Well, it depends on this, right? N. So for example, when n was 3, then each one of the products had 3 variables in it, either an A or a B, right? So let's just observe this. So now, that over there, this can be expanded. This can be expanded into products. Into products. Each with n, so I'll say with, I'll just write without fully, with n variables. With n variables. So to be clear, this is one from each factor. So one from each one of the factors. So remember how we determined each one of the resulting products? Had one from A or B. We grab one from each factor. One from each factor. Where each variable is either A or B. Is either A or B, right? Now there's n factors, right? So we can say something a little better than just what we have down over there. As there are n factors, observe each of the products has the following form. Has the form as follows. So do you know how I went through and I increased A and then I decreased B, like I kind of alternated them based on K? We can do that more generally. Has the form A to the n minus k, B to the k, which is equal to as follows. A times all the way up to some number of A's. B times some number of B's. How many of these are there? well, each one of these is grad from some factor, right? So how many factors do these a's come from? There's n minus k factors that these come from. And then over here, we have k factors that we pick b's in. That's what all this is saying, right? So all of the ones that have this form look like this, where it has n minus k factors and k factors if you were to just commute them, right? So you can rearrange them so they look like this. The question is how many of them there are, right? But the point is that you could do this over each of the k values, right? So each of them has this form for some k, which is, you can take on the value 0, 1, 2, all the way up to n, right? So please remember that each of these products has k of its n positions assigned the variable b. Assign the variable b. What happens with all the other ones then? So if I have n positions, so you imagine I have n of them, some of them go in b's, right? So what goes in the blanks? A's. They all get filled up with a's by default. Well, if k of them are b's, then n minus k of them, as you might suggest from this, each of these products that would take on a form like this, well, you can think of each one of these like a group of these products, right? And I want to know how many of them there are. So that's what we're going for next. So the remaining n minus k positions contain A, right? Now, let's ask a question now. Based on what we just described, if I look at each one of these groups of products, so I have the ones with k is equal to 0. I have the one where the k's are equal to 1, the ones where k is 2, k is 3, all the way up to k is n, right? So I want to know how many there are for each one. So for each k is equal to 0, 1, 2, all the way up to n, the number of products that contain B exactly k times is the number of ways to choose k positions from the n positions, right, to place variable b. To place variable b, right? What does that equal? If I have n positions, I select how many of them? K many positions to put b's in. So remember, think of it like a set where each one of the elements in the set is a position. And I pick k of them. So what is it? It's n choose k, right? Which equals n choose k. Now, very last step of this. Last step. Now we know how many for a particular value of k. So now we just got to consider all of them over k. All of the products. So to consider all the products, we have to sum over all values of k. Right? That's what a plus b to the power of n is, right? That's what the resulting expansion will equal. Therefore, by summing over k is equal to 0, 1, 2, all the way up to n, what does that mean? Well, it's a plus b is power of n, right? Remember, that's what we established already, right? Is that we can break it up into the factors, right? There's n of them. Then we realized, okay, each one of them has like a form that it takes on based on associative and commutative laws of algebra, right? Then we wanted to know how many times that appears. And we realized for each k, it's n choose k. So if I write this out carefully, in a much more fancy way, before I get to the fanciest way, the way that I want to prove the claim, let me write it out group by group. So it would be n choose 0 because this one has no b's in it, right? This one has one b in it. This one will have, next one will have two b's and so on. I'll go up to n choose k, which that would be a, where I have n minus k many a's, and then b, I have k b's, all the way up to n choose n. Sorry, I need to have some dots in here. There's more terms in between here. There's more terms in between here. I need the dot, dot, dot. It's very important. Plus, where I have no a's and all b's. But what's this? Let me write it out using summations. So let me use some notation. So I'm varying k from 0 up to n. So k is equal to 0 up to n. This is n choose k times, the general term of this would look like this. N minus k times b to the k. But what is that? That's exactly what we were trying to prove, right? Which we sought to prove. Which we sought to prove. And that completes the proof of the binomial theorem. So just remember, the big idea here is that we identify that this has that expansion, or it has, each one has each of the products, so it goes into an expansion of products. Then we know that each one of them actually has a specific form, and we wanted to know how many of them are there. So to consider all the products, I had to vary it over all possible values of k. And that's how I get the right-hand side. And then I simplified. Or refined it, I guess. The best way to put it. But that's the proof for the binomial theorem. Is there any questions about the binomial theorem? Any questions at all? So there's actually a deep connection between that row of Pascal's triangle and the binomial theorem. So the way you write out products of binomials, like say in the special case when n is equal to 2, you get the FOIL method. It's a special case of this theorem. That's the big thing. So next, what I would like to do is I would like to do some cases where I'm applying the binomial theorem. So that way you can see how we can use it in a few different settings. And then we'll lastly conclude by verifying that a row of Pascal's triangle is indeed a power of 2. So that'll be the last thing we'll prove, and I'll give you both a short, very, very short, arguably one of the shortest proofs I've given in lectures lately. So I'll prove it, and then I'll show you a combinatorial way of looking at the same thing. So kind of two ways of looking at the same guys. So I'm going to erase the boards, and then we're going to talk about how we can apply the binomial theorem. And then we'll conclude by proving that indeed a row of Pascal's triangle is indeed a power of 2. Or in other terms, it sort of is a special case of the binomial theorem. That's what I meant by implicit. It's rather implicit how we came about with it. Okay, so now, let's see how we can apply the binomial theorem. So let's apply the binomial theorem now. So previously we had seen the binomial theorem. It looks like this. So it was a plus b to the power of n is equal to the sum from k is equal to 0 to n of n choose k times a to the power of n minus k times b to the power of k. And this is true for all non-negative integers n and real numbers a and b. So from this we were able to get all sorts of different forms varying n. And I want to show you how you can apply this binomial theorem in a few different ways. So here's a few different ways of applying the binomial theorem. So the first one is I'm going to try applying it directly. So I'm just going to verify something that I told you to think about. Is you can just pick it for a particular value of n, and it'll give you the form that you're desiring. So, for example, if you picked n is equal to 2, you'll end up with the result of what maybe your teachers taught you how to do FOIL. And then you end up with the result of that. That form falls out of this theorem at n is equal to 2. So let's apply this directly. So I must stress that that's when a and b are equal, just to be clear. But anyways, we're going to try to see what happens with the binomial theorem if we fix n and then see what form we get by multiplying a plus b 3 times. So I have sorry, I'm getting really excited here. I need to calm down. I'm just so dang excited. So what I want to do is I'm going to fix n, and I'm going to simplify so that I can get a form that I can use to evaluate some polynomial, for example. Let's consider n is equal to 3. So this is something actually I asked you to do in a previous lesson. So let's try with n is equal to 3. So rather than having to compute n is equal to 2 and having to do all that work, I can use the binomial theorem directly. So k is equal to 0 up to 3 of 3 choose k of a to the power of 3 minus k, b to the k. So let's see what we get here. So I'm just going to write out for each value of k. So we start at 0. So we have 3 choose 0 times a to the 3. So a cubed, b to the 0 plus 3 choose 1 times a squared b to the power of 1 plus 3 choose 2 a to the power of 1 b squared plus 3 choose 3 of a to the power of 0 b to the power of 3, or b cubed. Notice I could simplify this further, but as I want to stress again, this is just a row in Pascal's triangle. So please just keep that in the back of your mind, these coefficients here. So I have 1 times a cubed times 1, right? B to the 0 is just 1, plus 3 times a squared times b plus 3 choose 2 is the same as 3 choose 1. So it's just 3 times a b squared plus, so a times b squared And then 3 choose 3 is just 1. 1 times a to the 0 is just 1 times b cubed. So let's simplify this now. We have a cubed plus 3a squared b plus 3ab squared plus b cubed. So if you ever needed to multiply a binomial by the exponent 3, it would have this form. If you try it with 2, you'll notice you'll get a very familiar form if you're familiar with the FOIL method. So as we discussed, it's nothing, there's no magic or anything about that method. It's just a way of remembering how to distribute terms. So let's see another way we can apply the binomial theorem. So we can figure out a and b carefully and then use the binomial theorem. So I'm just going to colloquially refer to this as figuring out a and b. So these are just a few ways to use binomial theorem. By no means is this the only thing. So we'll see another example of how we could use the binomial theorem. But let's consider this example. So suppose we wanted to derive a closed form. Wanted a closed form expression or formula. A closed form expression for the following. So suppose I want to have this for the sum from I is equal to 0 to n of n choose I times 7 to the power of I. So it's slightly different. I changed the variable from k to I just to make it clear that it doesn't have to be k or anything like that. It's just a name. So the sum from I is equal to 0 to n of n choose I times 7 to the power of I. Now, I want you to go back to over here. Notice that if I were to pick a and b carefully, I might be able to match the form I have over there. Do you notice that I have 7 to the I over there? That's like b to the k over here. If I were to somehow get rid of the a, then I can get something that looks like that over there, right? But what would I pick as a then? What's something that if I raise it to any exponent is always 1? Well, 1. One's a good place to start. Notice on the right-hand side, of the binomial theorem, when a is equal to 1, then we have this property that a to the power of n minus k is equal to 1. So applying the binomial theorem, by the binomial theorem, with a is equal to 1 and b is equal to 7, right? Because that's what the other term would be, right? That's what b to the k, this would be a 7 here. So if I want it to look like that, well, it tells you everything, right? Well, what does it say? The sum from I is equal to 0 to n of n choose I of 7 to the power of I is equal to the sum from I is equal to 0 to n of n choose I of 1 to the n minus k. So I'm just going to shove a 1 in here to make it look like the a over there times, sorry, not n minus k, we need n minus I. So same thing here. N minus I times 7 to the power of I. Miss Kitty, where are you? Okay. Anyways, the binomial theorem says that this is in fact equal to 1 plus 7 to the power of n, which if you simplify, this is just a to the power of n. So if you need a closed form for this. Well, I know, she was sort of having a great battle with Mauchi just a little while ago over there. It was pretty epic. But yeah, no, so that's a to the power of n right there. So that's a second example. Let me show you a third one. This is more for those that are the algebra enthusiasts. Is that if ever you have something that looks kind of like the binomial theorem, we can kind of substitute parts of your expression into it if it has the conditions of the binomial theorem. So let's try a third example. So the third example here, I'll just refer to colloquially as fitting the form. So fitting the form. So I'm going to give you something that does not look like the form of the binomial theorem. And then I'm going to show you that you could just actually fit it carefully in, and then you simplify. So watch this. So consider the expression for variables x and y, 2x minus 3y squared, like this. Now, at first, this doesn't look like anything resembling the left-hand side of the binomial theorem, right? It doesn't really look like it. But it actually is hiding that form in here. So rewrite, because remember, the theorem says that as long as it takes the form of a plus b to the power of n, where a and b are real numbers, we're okay. So we're going to rewrite that guy like this. So I can take anything that's like a difference like that, and I can replace it with addition where I negate. Like this. So I have 2x plus minus 3y. So it's the same thing, right? Squared. Right? You would agree with me that taking away is the same as adding what you're going to take away. Right? So I'm just simply saying, hey, look, instead of just straight saying take it away, I'm going to make it so that you have to add what you're going to take away. Meaning that you're going to anyway take it away. But I'm just doing it over this so it looks more like the form, right? So now I have something that looks like an A and something that might look like a B. So what I'm going to do is I'm going to let 2x be A, and I'm going to let minus 3y be B. Because this will work because A and B, as long as they're real numbers, we can use the binomial theorem. So applying the binomial theorem, and we're going to use it when n is equal to 2, right? Because the exponent was 2. With n is equal to 2 and a is equal to 2x, b is equal to minus 3y, we end up with this. Minus 2x plus minus 3y squared is equal to the sum from k is equal to 0 to 2 of 2 choose k times 2x raised to the 2 minus k multiplied by minus 3y to the power of k, right? If you're not convinced that that is the form, just put a and b in and see if it matches up with what you'd expect. Okay. Now, next what I'm going to do is I'm going to expand this out term by term, varying on k. So I have 2 choose 0 times 2x to the power of 2 minus 0 times minus 3y to the power of 0 plus 2 choose 1 times 2x all together, right, 2 minus 1 times minus 3y to the power of 1 plus 2 choose 2 times 2x to the power, so this, remember, it's all together, 2 minus 2 times minus 3y to the power of 2. So 2 choose 0, that's just 1, right? So this is just end up being, okay, and also minus 3y to the power of 0, that's also 1, right? So this is 1, 1, so you end up with just 2x all together squared, right? Now, 2 choose 1 is just 2, right? Then this is just 2x itself, right? Because it's raised to the power of 1. And then I have minus 3y raised to the power of 1. So I have 2 times 2x times minus 3y plus this one, 1 times 2 minus 2, that's 0, right? So this is just going to end up being a 1. And then we just have minus 3y squared like that. Minus 3y squared. Now, got to remember, if we square something that's negative, what it happens to it? It becomes positive. Well, I'm going to carry in the square here, so I'm going to square this, square that. So I have 4x squared plus, now we have 2 times, so we got 2 times 2, that's 4. So we have 4x times minus 3y. So I have 4 times minus 3 is minus 12, right? But it's multiplied by x and y, so it's minus 12xy. And now remember, minus 3y. So remember, this is y squared times minus 3 squared, which is 9, not minus 9. So it's plus 9y squared. So now we've received a form based on this. So this is how you could expand using the binomial theorem. So sometimes you might want to try fitting the form into the binomial theorem. Pretty nifty stuff, right? So next, so first, are there any questions? Any questions at all? Because we're going to move into the very last thing for today's lecture. So I'm going to answer that question that I've been leading on for the last hour of how do you know that the sum of a row in Pascal's triangle is a power of 2? We're going to answer that question next. And it's surprisingly easy to prove once you have the binomial theorem, because the binomial theorem tells you straight up when you plug in certain values. Because remember, the coefficients of that appear in the binomial theorem are a row in Pascal's triangle. So if we can answer that, then we can answer the question. Because the binomial theorem has those coefficients in it, it's just that we need to plug in the right values. And it becomes surprisingly easy to answer the question. I'm just going to switch markers here. Cross my fingers, we're going to be dealing with a good one. Okay, this will go. This will do. This will do. So let's proceed now. So in a previous lesson, I had alluded to the idea that in Pascal's triangle, that the sum of a row in Pascal's triangle is a power of 2. I'm going to answer that question now using the binomial theorem. So just to tell you what we're going to prove. So this is a very common closed form, regardless of its meaning within Pascal's triangle. And we're going to prove this. First, we're going to use the binomial theorem to do this. And then I'm going to give you a different way of looking at the same thing from a combinatorial point of view. So here's a theorem. For any non-negative n, specifically, I should say non-negative integer n, the sum from k is equal to 0 to n of n choose k is equal to 2 to the power of n. Now, you might be staring at this like, okay, so how does this answer the question? Well, just as a quick reminder, let me remind you of what Pascal's triangle looks like. So I got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. So my claim previously, and remember, that comes directly out of this theorem, what we wanted to know about this, because in a previous lesson I told you that if you add up the rows, so if I sum up these numbers across the rows, if I add them up, each one's a power of 2. So I have 1, 2, 4, 8, 16, and so on. Why is that? Because each one of these rows is this sum. So let's prove it now. So this is going to be an algebraic proof. But remember, under the hood, we had a combinatorial argument for this, but you can go about it in other ways as well. So applying the binomial theorem, so what should I apply the binomial theorem with? So remember, the binomial theorem has this form, right? A plus b to the power of n is equal to something that looks kind of like that, but it has like an a times a b where each one has exponents in it. In a previous exercise, we noticed that if we just put 1, as a, for example, you end up with just something that always results in 1. So why don't we try something that'll make it sure that this is 2 to the power of n. So maybe make a1, b1, and we'll see what happens. With a is equal to 1 and b is equal to 1. So we end up with this. So now, 2 to the power of n. So I'm starting on the right-hand side. This is equal to 1 plus 1 to the power of n. But this is equal to the sum from k is equal to 0 to n of n choose k of 1 to the power of n minus k times 1 to the power of k, right? That's what the binomial theorem says. Then this is just 1 always. That's 1 always, right? So this is just times 1 times 1. But then this is all just this. The sum from k is equal to 0 to n of n choose k. And that's it. That's the proof. Very short, very simple. So that's how you could prove this claim that the rows of Pascal's triangle are in fact powers of 2. Comes out of this theorem. But now I want to give you another way of looking at the same thing. Namely, I want to address this from asking a question about numbers of subsets that are possible for a given set n. Now, when I say n, I got a little excited there. What I should say, imagine you were given a set with n elements in it. That's where I wanted to go with this. Yes. So imagine you're given a set with n elements in it, and somebody asks you how many subsets are possible with that given set. Well, let's first ask that question and see where it takes us. So I'm going to consider a combinatorial view of the same thing, okay? So consider a set with n elements. So consider a set with n elements. So what I want to do now is I want to consider all possible subsets. So that means I'm going to consider the subsets of size 0, 1, 2, 3, all the way up to n. So we consider subsets of A with k is equal to 0, 1, 2, all the way up to n elements. It's size, right? So I want to quickly derive something with you. I'm not going to give you a formal proof for it, but you could prove it with mathematical induction. But I'll give you an explanation using the multiplication principle. So I want to know how many subsets there are of a set with n elements. So this equivalently can be phrased as another question. So how many elements? Equivalently, we're talking about subsets of this set. How many elements are in the power set of A? So the power set of A, for those that aren't acquainted with the power set, is all the subsets of size 0, 1, 2, 3, all the way up to n. So that's what the power set is. So how many elements? That's the same as asking how many subsets there are of a given set. So this is just a set that contains all subsets of A. So it includes the empty set. Just remember, that's a subset with size 0. So all of the subsets. So now I want to answer this question. So how many can there be in this set? So we consider the ones with no 1, 2, 3, 4, all the way up. So either an element is in a subset or it is not, right? So if I have n elements, so suppose I want to consider the subsets of size 0. There is only one, right? But naturally, beyond that, when I include, so I want you to think of it being like I have two buckets here. Two buckets. I have this bucket. This bucket says it's in the subset. This bucket says it's not in the subset. I'm going to describe this as a process. So I consider the first element after this. It either can go in the subset or it doesn't go in the subset. So for example, it could go in the subset. So how many possibilities can there be for the first element? It can go in this bucket or this bucket. But there's two choices, right? Now, when I consider the second element, it can either go in this subset or it doesn't. So I could completely determine a subset by making choices of either putting it in the subset or not putting it in the subset. Again, two possibilities. So when I had two original choices, when I introduce two more choices, it's that I include this element in the subset and this element either in the subset or not in the subset. So in this case, maybe I put them both in the same subset. So how many possible subsets can there be of two elements? Well, there's two possibilities at first, then another two possibilities. So there's 4 possible subsets that could exist, right? So if I did it with 3, I could completely determine a subset by picking whether it goes in the subset or it doesn't go in the subset each time. There's 2 possibilities each time. So in the third case, maybe it doesn't go in the subset. So you can imagine I have a set with 3 elements. First 2 go in here. Third one doesn't go in the subset. You can completely determine every single subset by going through a process like this. But what did I actually do? I chose 2 possibilities for each one of the elements. So either it goes in the subset or it doesn't. I do this n times, so how many possible subsets can there be? Or in other words, how many elements are there in the power set of A? How many are there? Think back to the multiplication principle. So we pick n elements to each go in or not go in. So that's 2 choices. And we do it n times, right? So there are 2 to the n possible subsets, right? Or equivalently, the power set of A has 2 to the power of n possible elements in it, right? As its cardinality or size is 2 to the power of n. So in other words, if I denote the power set of A as that with a fancy p, and I ask how many elements it has, this is equal to 2 to the power of n. That's true if it has no elements as well, right? Because the empty set is a subset. So if I have 2 to the power of 1, what am I got here? So I have, so if I have, just trying to think off the top of my head about this. If I have 1, actually no, this is, oh yeah, no, wait, I got this slightly off. It's 2 to the n plus, let me just think here carefully. Let's think. If we have no elements, the power set would just have this, for n is equal to 0, n is equal to 1. It should have the empty set and just that element. So suppose it's just A, n is equal to 2. We have empty set, A, then you would have B, so the second element, and then you would have AB. Yeah, we're all correct. For some reason I was second guessing myself. But yeah, no, so the size of the power set is 2 to the power of n. Now, since we've derived this using the multiplication principle, I remember, like I stressed, you could use mathematical induction to prove this set theoretically, but I'm not going to do that here. Instead, we're just counting stuff. So now what I want to do is I want to compare what I did here with a combinatorial way of looking at these subsets and see if we can come up with the same thing. Sometimes you guys freak me out. Just okay. Now I want to connect this up with the binomial theorem. So now that we know that the size of the power set, or equivalently the number of subsets of a given set A, is 2 to the power of n, I now want to connect a question related to this to the binomial theorem. So what is the union of the following? So I'm going to imagine these all as their own sets, and I'm just going to try to dump them all together. So all the subsets of size 0 of A, all the subsets of size 1, all the subsets of size 2, and so on, all the way until we consider all the subsets of size n. Now, you might be looking at this and saying, what the heck are we looking at? So remember, these are all the 0 combinations, these are all the 1 combinations, these are all the 2 combinations, these are all the n combinations. So please keep that in the back of your mind. So how many elements are there in the power set? So if we have this question in mind, I want to remind you what the power set definition is. So this fancy P with the set A, this is the same as me saying that if I have all the subsets of size 0, so these are all the subsets of size 0, these are all the subsets of size 1, these are all the subsets of size 2, and so on, all the subsets of size n. That's what the power set of A is. Then, please note that these subsets are all distinct, right? But specifically, they're also, each of these is actually a disjoint set. So what can we say then? Well, we could use the addition principle to count these, right? Because the power set is indeed a disjoint union, so it's just all of these, all these are pairwise disjoint, correct? So if I add up all of these, in terms of the numbers of them, that tells you what the size of the power set is, or the number of subsets there are. So then, the size of the power set of A is equal to the cardinality or size of A0 plus the size of A1, and so on, up to the size of this set AN. So that's just from the addition principle. Now, when we think about it, this is all the subsets of size 0. These are all the subsets of size 1, and that all the way up to the subsets of size n. But what is this? Well, like I said, this is counting. This is counting all the k combinations for k is equal to 0, 1, 2, all the way up to n. And what's this? Well, look. Well, that means this guy over here, this equation I just derived here, it means this too. It means n choose 0 plus n choose 1 plus n choose 2 plus all the way up to n choose n, right? But this is awfully fishy, right? We already know that this is 2 to the power of n, right? This is 2 to the power of n. We derived that earlier using the multiplication principle. Then the sum, so I'm just going to write it in some summation. Then the sum from k is equal to 0 of n choose k is equal to 2 to the power of n, right? So this is another way to derive the connection that we established in our previous theorem. This is because we knew that the size of the power set is 2 to the power of n, and we can, in a combinatorial fashion, represent all of our subsets and how many there are in this fashion. But this is just another way of looking at the same thing. So this is another way you could figure out that this theorem holds. But yeah, no, so we answered 2 things there. Actually, no. Specifically, we addressed the question about Pascal's triangle, but also we've seen how we can connect up the binomial theorem in this special case when A is 1 and B is 1, how it connects up to thinking about things in a combinatorial way, the underlying structure that we were trying to allude to some while back. Are there any questions? Any questions at all? So this is another way you can prove the theorem that we had. So this one is based on knowing that the size of the power set is 2 to the power of n. All right, any questions? Any questions at all? We've been going for now like almost 3.5 hours, something like that. And, yeah, about that, yeah. But if there aren't any questions, because I don't see any questions, we just sort of had some comments about Miss Kitty, which Miss Kitty's around here somewhere. Mochi and Miss Kitty sort of had a battle over things. I had to take away Miss Mochi's bell because she got a new collar with a bell on it. I had to take it off because she was being a little extra loud. But if there aren't any questions, at all, we're going to stop right here because I got nothing else to cover for this week. When we come back next time, we'll either talk more about combinatorics here, or we're going to come back to automata theory and theory of computation, and we'll explore the idea of non-determinism. So, specifically relating to finite automata, just to be clear. We're not going full-blown crazy with clairvoyance, okay? But we need to talk a little bit about what non-determinism means, at least in the context of finite automata. So we'll probably do that. But if you enjoyed this and you're watching this in the future, I'll say thank you for coming on by. And of course, if you enjoyed this, be sure to like or share this with your friends. And of course, if you want to support this work and help keep the lights on, please support at patreon.com/pagewizard and look out for updates. I usually am quite regular with my uploads. So I'll say thank you so much and have yourself a beautiful day. I'll see you later.